So here's our topic. The last topic we have in chapter 6 is going to be this notion of Newton's second law with non-constant forces. As we discussed, the entire thing that we're going to be doing here is getting to the point where we can do our substitute, separate, and integrate. That's our goal. And so the goal here, or rather that's the goal, what we have to do in any given situation then is to try and fit what we need into a form that we can do this process for. So what I want to do is first talk about some physical situations with non-constant forces, because those are going to be critical. So I think the first and most obvious situation is air resistance. Now, air resistance is a subset of a class of forces, and technically that class of forces is actually called fluid resistance. It is the same general force that acts whether it is that I'm trying to move through air or I'm trying to move through a liquid. Those are both fluids, right? So let's talk about that force. So we know that that force, we tend to use Fr because technically this is a resistive force, whether it's air or fluid, is occurring because you have your object that's trying to move through a fluid. And so since it is colliding with the molecules of that fluid exerts a force back on the object. So it's really Newton's third law that yields all fluid resistance forces. So what factors affect this force? Well, the main factor that affects this force, and we've discussed this in the past, is how fast you're going. Because the greater the rate of which you're moving through the fluid, the more particles per unit time you encounter, therefore the larger aggregate force that comes back. So what we're going to have here is a symbol, or rather something then for that velocity. Now, also most importantly here is, remember, this is a vector, right? The fluid resistance force is always going to act in the opposite direction as the relative velocity of that object through that fluid because of that Newton's third law analysis. So I'm going to put in here is a negative sign, right? Because whatever the direction of the velocity, the fluid resistance force acts in the opposite direction. So this ends up being just a little bit tricky here because notice here I haven't made a declaration, right? What this says though is if my velocity is to the right, the fluid resistance force must be to the left. If my velocity is down, the fluid resistance force is up. If my velocity is east, the fluid resistance force is west. Whatever it is, that's always true, irrespective of the declaration. So we're going to see how we're going to deal with that in a couple of minutes. Now, other things that matter here. Well, there's a bunch of physical things that matter. The density of the fluid matters. The viscosity of the fluid matters. As well as the frontal surface area matters, right? If you have a larger frontal surface area versus a smaller frontal surface area, all those things matter. In this class, we're just going to lump all those ideas into one constant, and that constant is B, right? So this constant deals with the density of the fluid. It has to do with, as I said, the frontal surface area. It also has to do with the shape of the object beyond frontal surface area, right? Like we know things that taper to a point versus other weirder shaped objects, even if they have the same frontal surface area. That thing that tapers to a point, like the nose cone of a plane, is going to be more quote unquote aerodynamic. So anything you think of as more aerodynamic would have a smaller b, right? The larger b is, the greater this resistive force at the same speed. So. And then what we're going to do is we're just actually going to put an N here because in weird situations, specifically when you have highly viscous fluids, sometimes this speed or this velocity is raised to a power, whether it's 1.5 or 2 or 1.7, whatever it is. Now, we're going to pretty much stick to the integer values, and for the large part, N will be 1 in most examples. Because for an object going through the air at fairly normal speeds, N is 1, right? Or at least that's our experience. So this is the air resistance force, and we'll see how that plays out, because that's the main example that I'm going to do for us in a couple of minutes. Another force that varies as a function is the spring force. And hopefully you saw this last year, that the spring force is always dependent upon how far that spring is from its what's called natural length. So if I have a spring here that's attached to a wall, and that's how it is when no forces are attached to it or acting on it, that's what we call the natural length, L0. So then what happens here, if I stretch the spring, what we say here is we create a system of a coordinate system where we make the natural length of the spring where that exists x equals 0, so that this position here where I'm stretching the spring to, or if I'm compressing the spring, right, that's a deviation, that's a position relative to the natural length. And so we're going to have that x there. Now, it doesn't need to be x. It could be a y, it could be z, whatever, or just a generic s, but it's a position. Now, notice here that if I say to the right is positive, here the spring has a positive position, but it would be pulled back towards this x equals 0, the natural length. So the force is going to be opposite the direction of the position away from the natural length. So when I compress the spring here to the left, the position here is going to be negative, and the force would be positive. So much like in the resistive force, this thing has a naturally occurring negative sign that floats in it. Now, we're going to do this a little bit more specifically when we hit this in chapter 7, but that's good enough for now. And we'll say that there's a constant here that we call K, and as a spring constant, you should have learned about that last year, that different springs have different stretchiness, right? The larger K is, the less stretchy it is, the harder it is to stretch it. You may remember this. This is something that's called Hooke's law. And most springs obey Hooke's law. In fact, most elastic objects obey Hooke's law within a range. And sometimes when you mess things up, like we got the power here with the velocity, we end up with a power here on this as well in some weird situations. But it should note that position is a vector. So I've got a vector here, a vector here, and these two vectors are always in the opposite direction. So once again, that's going to play out. Okay. Two more situations that I want to point out. So if this is the Earth, here is some sort of the moon going around, right? So the force of gravity. The force of gravity is dependent upon the position. And you should have learned that last year, Fg, right? Now notice that no matter where your moon is, Fg is going to act radially inwards. So in a polar coordinate system, we're going to define radially inwards as negative r hat, right? In the radial direction, but negative means inwards. When we did our work with coordinate systems, we defined that. That gravitation force between the moon and the Earth is equal to negative big G m1, m2, in this case Earth and the moon, over how far from center to center it is, r, and then in the r hat direction. Okay. So that also, actually r squared, excuse me. So here's another place where the force is a function of position, right? And in very particular, that negative sign pops up there because it's always that radially inward. We'll deal with that much later in the year, but I wanted to give that an example, right? And the last thing I want to bring up is, let's talk about, say, for example, a mouse on a string. We know that's going to oscillate back and forth like this, like a simple pendulum, okay? Whereas here, the force of gravity and the tension, this is going to have a radial component, FGR, and it's also going to have a tangential component, FGT. And that tangential component is going to be a function of what that angle is. So as this thing swings in, that angle is constantly changing, which means that this force is constantly changing. And so we'll look at that example as well. So those are 4 very simple and practical situations in which there are non-constant forces acting on something. I don't even have to get very weird with all of this just to make something up, because in most of our experience, we were actually dealing with non-constant forces, and all the work we've done with constant forces are really kind of, the not the rule, they're the exception. But I'm going to show a methodology of how we approach this problem or these types of problems with the resistive force of air resistance. And what we're going to do is we're going to do the skydiver problem, right? Or just like the someone jumping out of a plane. So initially, there's your object, and it's going to begin to fall. So we know initially at t equals 0 that the gravity force is acting downwards. Initially, there's no air resistance force. Assuming, let's say this person jumped out of a helicopter, so their velocity is 0 initially, VI is 0. Now, we all know that that's not true because normally people jump out of a moving plane. It's insanity. Having done it, never will do it again. It literally is insanity. You're not at rest when you jump out of that plane because that plane is going like 100 some odd miles an hour horizontally, right? So you jump out of that plane, you're going a couple 100 miles an hour horizontally, and then the vertical starts, and it's horrifying. Anyhow, let's just say that this person drops from rest. So at some time later, so t equals some time later, but not that much later, force of gravity is constant, but this air resistance force begins to act upwards, right? And then over time, what ends up happening is that air resistance force grows because as we think about this over time, we know that there's a net force downwards, right? Because if I were to look at a net force equation, so let's just do that very quickly. And this is where it gets a little tricky, right? So if I do a net force equation in the vertical direction, that's going to equal MAY. Now, it's very tempting to want to do the following. FG minus FR equals MAY. But that's going to be problematic. So why problematic? Well, let's go back over to this. The definition of the resistive force encodes this negative sign to this. So when I assign directionality to the beginning of the force there, that's problematic. Anytime you're dealing with something like a resistive force, or you're dealing with the spring force down here, anything with encoded directionality in the equation of the force, we're not going to apply the declaration to the force when we're doing our sum of forces equation. So that's really important. I want you to write that down. I'm going to write that down here. So when dealing with forces that encode directionality in their equations, do not assign directionality. And the reason for that, folks, is very simple. The reason is because when you develop your equations, when I plug in for the velocity, like let's say to the right is or like here, I say down is positive. When I plug into the velocity here, I would plug in a positive number. Notice that makes the resistive force upwards. If my object was moving upwards, that would make the resistive force downwards. So we're going to be applying directionality into the velocity of this equation, which will then change FR to the sign I need it to be. Same thing here, down here in the spring force. When I plug in the position, the sign of the position will tell me the sign of the force. So I don't want to preemptively determine what the sign of the force is, since it's something inside of that equation that's actually going to determine that size. Okay, so let's look at this expression here. So plugging in mg minus bv equals may. Okay, so I did an n of 1 because that's normal situation. So let's look at this. Mg is a constant, yes? That means that initially my acceleration is going to be, well, the velocity is 0, and so initially my acceleration would be g, downwards. That makes sense. But over time, as v increases, mg minus bv decreases. That means the net force is going to decrease, which means the acceleration is going to decrease. But notice here, no matter what, my velocity is downwards and my acceleration is downwards. Therefore, this object is going to speed up because the velocity and acceleration are in the same direction. But because a decreases over time, therefore, the rate at which I speed up decreases. Another way to say that is the first derivative of the velocity is going to have the same sign as the velocity itself, but the second derivative of the velocity is going to have the opposite sign as the acceleration, right? And so that's what, so this velocity is increasing decreasingly. So that work that we did at the beginning of the year, and that's encoded in this equation, right? Now, a couple things from there, because that's an interesting little equation, and we'll get back to that in a minute. What's going to eventually happen here is that this object will speed up to the point, so this term will grow until it matches the mg term, and then this thing will stop accelerating. So what is that called? Hopefully you've heard of that. That's called the terminal velocity. And so terminal velocity. Terminal velocities occur not just with air resistance, but terminal velocities occur anytime you have a driving force and what's called a retarding force, right? So you have a driving force and something that is trying to slow the motion down. I know that that word sometimes is something that people are like, oh, don't use that word. It's actually what is called in the physics language. So I just wanted to use that there, but that's what it is. I will just say now resistive force. That's the new parlance. So when I have a driving force, in this case gravity, and a resistive force, in this case air resistance, oftentimes the conjunction of these ends up with the terminal velocity, which is a max velocity something can have when the driving force and the resistive force balance out. So this is our max speed, or well, our max velocity. There it goes. And it's going to occur only when the acceleration goes to 0, right? That's the idea. And so what I'm going to do here is I'm going to take the limit as either a approaches 0 or as v approaches v ter. And that's a symbol for it, v ter. We don't use vt because we're using that for tangential velocity. And so what happens here, I've got mg minus bv ter equals 0. And in this case, v ter is equal to mg over b. That means more massive objects will eventually get to a higher speed, and more aerodynamic objects with lower b's will get to higher v ters. So there it is. Now, I'm not boxing that as an equation because based on the type of force that is the driving force and the type of force and the structure of the force that is the resistive force, right? And those could be all different things. The equation for v ter is unique to that physical situation. So there is no one equation for v ter. It is contingent on the scenario. But how do you find a v ter? You do a sum of forces equation, you do a limit analysis as a approaches 0, and you find out your expression for v ter. There you go. Now, what our goal though is I want to find the velocity as a function of time. So I'm going to bring back that equation, mg minus bv is equal to may. Okay. Now, I mean, I don't really need that y subscript there because then technically I should use a y subscript there as well because it is a velocity in the y direction. So actually, let's just get rid of that for sake of ease. Now, notice here what velocity is a function of time. In this equation, I've got velocity, right? I don't have any times in. So I want to have an equation that has just velocities and times. So what is a person to do if they have an expression and they want to find another expression? And everything is dealing with these changing concepts. So what is a person to do? That symbol or that hand gesture means substitute, separate, and integrate. Now notice here, I have a couple of things I can substitute. I can go v is equal to, in this case, dy dt. Not very helpful because that introduces a y into the equation, not what I'm looking for. And I know there are 3 different things to put in for any acceleration. The first is the first derivative of velocity with respect to time. So that is a vy there, technically vy, ay, right? I'll just be a little formal over here on the side. Vy dt. Okay, great. The second substitution we said was the second derivative of the position with respect to time squared, right? Or d squared y dt squared. Not helpful in this case, but it's good to review. And then the last thing we said was v dv d position variable. So since this is ay, this is vy dy, right? Now, if I'm looking to do velocities and times, the clear winner here is dv dt in place of y. Now, I just wanted to put all these out there just to remind you of the work that we've done. So let me move this over a little bit further to the left here. So mg minus bv is equal to m dv dt. So what do I have there? Well, what we have there is a first order differential equation, right? And we talked about these before. First order because the highest order of derivative is the first differential equation because it's got a derivative. So for those people interested in taking the AP exam eventually, oftentimes they ask you to write the differential equation that you would solve in order to do this. Boom, I've got it there. If they say, write the differential equation in proper form, that has a different format. The proper form here would be to put the first derivative first, get no coefficient in front of it, so I didn't need to divide through by m, right? And then I would need, so if this is a v, the next term would be the v term, and this would be added over onto the side. So plus b over mv, and then anything that doesn't have v's would be left on the other side. That's actually the equation in proper form. Now that's not helpful for solving the problem, but that is the equation in proper form should they ask for it. But if they just say write the differential equation, that's what it is. If they say write it in proper form, that's what it looks like. So I'm just gonna, that's not what we want to do because I actually want to solve this problem. So once again, our goal is to find v as a function of t. So I've now substituted. So the only variables in this problem now are v and t. M, b, and g are all constants. So fantastic. So next what I need to do is separate. And that means I need to get all of one variable on one side, all of the other variable on the other side. So I need to get all the v's on one side and all the t's on the other side. And so the hard part about this is this mg term, because it neither has a v nor has a t in it. But notice here when I put in proper format, I didn't separate because this v is still attached to that t. Now notice here, if I just multiply the whole thing by dt, that attaches a dt to the v, which is not helpful as well. So it seems like I need to be a little bit more clever with this. So the way that we're going to do this is the following. If I want to substitute this, what I want to do here is cross multiply. I'm going to take this dt and put that up here. And then I'm going to take the entire damn term, mg minus bv, and bring it down to the denominator. Now, there it is. It's not the nicest looking thing, but that's what that looks like separated. I've got all the v's on one side, I've got all the t's on the other side. Now, something else that we can do here, and actually I would recommend this, is this having the m in two different spots, I think is a little messy. So let's just multiply both top and bottom by 1 over m, right? Because that yields a slightly nicer expression of g minus b over mv. Now, someone's saying, Vaughn, you're a hypocrite. That is a complex fraction. Right, but that's also not our final answer. So it's fine to have complex fractions in your intermediate work, but just never leave a final answer like that. So we have substituted, we have separated, and now we're going to integrate. And folks, none of this indefinite integration crap. It is not helpful. In physics, we do definite integrals because I know I can start the clock at 0 and go to t, right? In this situation, I told you we started at rest and we're trying to find velocity as a function of time. Done. If I don't start at rest, I just make this vi, right? But at time, you always have the power of saying when time is equal to 0. So there it is. Yeah, like just indefinite integration it's a cutesy sort of thing that you can do in math class, or in a generic problem that you don't know enough about the physical situation in physics, you go like, I guess I'll have to do it. But I mean, geez, you want to just avoid doing it so badly. It's just poor. It's a poor idea. So here the left integrates pretty easily into t, but here, oh geez, what am I going to do? What are you going to do about this? Well, if I look at this, I see that I'm going to have to do a u substitution. So I'm going to let u equal g minus b over mv. And I'm going to then do that substitution. So I can see I've got dv over u, and that's nice. So now I need to deal with this dv. So we're going to go du dv is equal to, well, that first term goes to 0, and this is just negative b over m. So du equals negative b over m dv. It's easy to find my negative b over m. Just to make this a little bit easier here, right, technically I have to do negative b over m, negative b over m, and there is my du. So if we look at what we have left mathematically, then I've got t minus 0, because there's no reason why we can't advance the left side along in the math, is equal to integral from 0 to, now I'm just going to 0 to v. Now we've done the transformation to u, so we're not going to plug in those limits since we're changing to the u now. And I'm left with du over u, and I know I've got this negative b over m in the denominator, so I'm just going to flip that up top to be negative m over b like that, and that's just easy to deal with. So let's now do that. So t is equal to, and this becomes d over u is just the natural log of u, so nice and simple there. So negative b over m natural log of u. Okay, so what I'm going to do here, we'll evaluate it between two things. But first, I want to substitute back in what u is equal to. And I want to neaten this expression up because I'm going to move the constants over to the other side. So negative bt over m is equal to the natural log of g minus b over m v evaluated between 0 and v. Okay, I think it's just easier to have those constants over there in the first, rather now. So negative bt over m is equal to the natural log of g minus b over mv minus natural log of g, right? Because that second term goes away. So I've got two logs here. What I want to do eventually is combine them because I'm trying to solve for v here. So it'd be much easier if this side only had one term. bt over m is equal to natural log of, and we know that when we subtract, we divide. And so that first term becomes 1, so g over g minus bv over mg. Okay, which is a nice little expression there. So what do we do with this? Well, we raise both sides to the e because I'm trying to solve for that v, and I've got e to the negative bt over m is equal to 1 minus bv over mg. Okay, so once again, trying to isolate the v, I'm going to bring the bv over mg over to this side and move the e to the negative bt over m over to this side. So I've got bv over mg is equal to 1 minus e to the negative bt over m. This is where I say stop, because that is a good thing. Why is that a good thing? I told you back when we were talking about non-constant accelerations that the structures of e to the something t, e to the negative something t, and 1 minus e to the negative something t were structures that come up all the time and that you had to know the graphs of. So just to review, e to the something t had a shape, has a shape like that. That's your exponential growth. E to the negative something t was your exponential decay. And then your 1 minus e to the something t, or e to the something negative t, has this shape, where it has a horizontal asymptote, just to remind you. So we're getting that horizontal asymptote, and that's going to be great. So solving this, we have one last step. V is equal to mg over b, 1 minus e to the negative bt over m. There you go. Now, I'm never going to give you this exact problem again, but this is a nice structure and flow so you can see the steps that are expected. So let's look at that result. Mg over b, that's familiar. Yeah, it should be very familiar. Boom, step 1 here, that's the terminal velocity. So I can rewrite this equation that v is equal to the terminal velocity, 1 minus e to the negative bt over m. So look at that expression. Take the limit as t approaches 0. When t approaches 0, e to the 0 is 1, the velocity is 0. Cool, at t equals 0, we had a velocity of 0. That was what we started with. Yay. Next, what happens after a really long time? Well, after a really long time, we take the limit of this expression as t approaches infinity. So e to the negative infinity, that term goes to 0, and the velocity just becomes the terminal velocity. So this shows over time that as time goes on, it approaches the terminal velocity, meaning that this asymptote here is the terminal velocity. Boom, there you go. And that's actually a very common structure that happens in all problems where you have a driving force and a resistive force, and there's a push and pull and a tug between those. Now let's say I wanted to know the position as a function of time. I'm not going to do it because it's just grunty math at that point. But I would just do the next substitution, in this case, dy dt is equal to that expression. You can see it's very easy to separate. The dt goes onto the other side, and then I just have to do that antiderivative, which is actually a fairly simple antiderivative, but I don't want to waste my time with that. But that's the general structure of these problems. Take Newton's second law, figure it out, write the differential equation. Hopefully you can separate that differential equation. I want to show you one more example, and that's that last example we were looking at, okay? Because this one's just a doozy. It looks like it should be really simple, but it's not. And it's going to set us up for like, oh God, I never want to do that again. There must be a better way to do it, and there's going to be. So I've got my force of gravity going down here. Let's say that this is deviated from the hanging down vertical by theta. I know that I can separate this into a radial component and a tangential component. And so that tangential component is going to speed this object up as it goes around the arc. And that's going to be weird because what we have to deal with, folks, is not x or y. We're going to have to deal with that tangential direction. So I want to remind you of a couple of things. That arc has a length of s, right? That is our position along the tangential arc. So this is like my s is equal to 0 point. So hopefully you remember from like freshman math that s is equal to r theta, where theta is in radians, and r is the length of the radius. Now, this is only going to work here for our situation because the radius is constant as long as I'm going on a circular arc. This gets a lot more complicated when it doesn't go along a circular arc, and we will explore that on another day. So here, what do I have? Sum of forces in the tangent is equal to MAT, right? Let's say I'm making this way positive along the tangent. Okay, so that would mean that this plus FGT is equal to MAT, okay? Everyone good so far? All right, that has a really weird implication that we'll get into later. It's not going to be important for this part of the problem. Yeah, we'll just talk about it. So here's the thing though. What direction is positive? Notice this thing is starting at a negative s because I said this direction was positive in order to get the FGT positive. Notice here, theta then is negative as well because I'm starting at a negative theta. So that's going to become important in a couple of minutes. So what am I going to do here? I'm going to do negative mg sine of theta is equal to MAT. So nice and easy there, m's cancel. So I've got g sine theta equals AT. And geez, what do I do with that thing? Because I've got theta and AT. Well, I literally just threw my pen. So thinking back, our tangential acceleration, well, that's either going to be dvt dt. It's either going to be d squared s dt squared, because that's the position variable that matters, or that tangential acceleration is going to be vt dt, or excuse me, dvt ds. Okay? And if you look at that, it seems like none of our substitutions are going to get the job done, because I need a theta here. I don't want to turn this theta into something else, because then you have the sign of blah, right? I want to turn everything else into theta. So how could I do that? Well, the magic is up here. I can do that here. Notice here, ds, right? So what can I do with that? Well, this dv/dt is not going to help me. So I need to do substitutions in order to make this work. So what I'm going to do here is say, well, tangential speed, what's that? Well, that's just ds dt, right? Well, I can then apply that derivative to this expression. Now, here's the thing, and here's where it gets real tricky. As long as the radius is constant, that's going to pull through that derivative. So ds is going to equal r d theta dt. That's going to become important, or ds dt is equal to r d theta dt. And we'll deal with that again later. But notice here I can divide through by dt, because it's just a ratio, so I can get rid of that. So this at now is equal to vt dv dt over r d theta, assuming r is a constant. Now, if you do this substitution, I have two variables, dv, or vt dvt over r d theta, right? And so I'm going to get gr sine of theta d theta is equal to vt dvt. And that is now separated, and I can integrate that. So what am I going to integrate from? Well, my initial position is negative theta, and maybe I'm trying to get down here to the bottom. My initial velocity would be maybe 0, and then I'm trying to go to v. And then I can solve that problem, right? And from here, it's just fairly trivial math. But that's a gross thing for figuring out like the speed of this thing along this arc. So last year, when you did this, because you did this, you didn't do calculus to figure out how fast the thing was going at the bottom of the swing. What did you use? Well, hopefully what you remember you used is conservation of energy. We're going to find that the Newtonian approach to curved paths is awful, right? It's just disgusting. So Newton does his work in what, the 1680s, 1687 publishes the Principia. And it's not until, a century and a half later that people start thinking, is there a better methodology for doing these things? Because the Newtonian method yields these really complicated integrals in the calculus and gets very messy. And that's where the concept of energy comes from. It's trying to deal with weird shaped paths and non-constant forces. And we're going to find that energy simplifies our life under very specific circumstances and takes us from these weird calculus things into a much happier place. But my point is, this methodology, substitute, separate, and integrate, was construct the sum of force equation. Notice that I needed to separate this, so I need to have everything in terms of two variables, and that's what all my work with my substitutions is doing, trying to figure out a way to get it to two variables, and there you go, I'm in two variables, and everything's golden. So let's actually might as well just finish this. I know on the left this becomes gr times negative cosine of theta evaluated between negative theta and 0, and this on the right, is equal to 1/2 vt between 0 and t, right? And so here I'm going to have gr negative cosine of 0 minus negative cosine of negative theta is equal to 1/2 vt, or 1/2 v. square, I forgot the squared there, excuse me, minus 1/2 of 0 squared. And so I've got GR and then cosine of 0 is 1, right? So that's going to become a -1 there, something, right? So that's going to become a -1, negative, negative. So what happens there? Cosine of theta. So that's what our initial position is. And so what does that end up being? Negative, negative is positive, but cosine of a negative angle is just the angle itself. So plus cosine of theta, and that's equal to then 1/2 v squared, right? So there you go. It looks a little bit different, and we can figure out what this is going to mean a little bit later and show how this simplifies to something that you're actually rather familiar with. But the methodology of substitute, separate, and integrate, how we deal with these non-constant forces, it is a unified method. Just sometimes it gets a little gross.